Hello, and welcome once again to Bedside Physics. Before we drift into the mysteries that await tonight, please consider taking a gentle moment to like this video and subscribe so that each time we explore the universe together, you can settle in without worry of missing a single calm discovery. And while you're here, I'm curious, where are you listening from? Perhaps you are lying quietly in a softly lit bedroom, the world outside still and hushed. Or maybe you're somewhere more bustling, with the subtle rhythm of a life pressing against the edges of your awareness. It is fascinating to consider that your location, your environment, and even the speed of life around you subtly tints how time feels. The seconds you perceive, the minutes you measure in thought, they are not quite the same as the seconds counted by a clock on the wall or the precise oscillations of a cesium atomic clock ticking billions of times per second. Time, in the way we experience it, is elastic. It stretches and compresses according to attention, emotion, and circumstance. In one moment, a single hour can feel like an eternity, while another day may vanish in what seems like a breath. Scientists refer to this felt experience as temporal qualia, a term that captures the phenomenological texture of time, the subtle, subjective quality that colors every moment. Mark Wittmann, a cognitive neuroscientist working in Germany, has spent years studying this internal sense of time, examining how neural circuits and psychological mechanisms combine to produce what we perceive as the passage of seconds and minutes. He explores how attention, memory, and emotional salience contribute to the impression that some moments linger and others flee. While the universe marches along according to precise measurable laws, our minds weave a tapestry of subjective temporal experience that often diverges from objective time. Consider the ticking of a mechanical clock, a pendulum swinging with exact regularity. Each swing marks a fraction of a second, meticulously steady. Now, contrast that with the moment your mind is fully absorbed in a task or swept into a novel experience. Those very same seconds, measured in milliseconds by the clock, seem to stretch or collapse. Researchers in cognitive psychology have demonstrated through countless experiments that human perception of time is sensitive to novelty and repetition. Novel events, those first encounters and surprises, tend to feel longer because the brain encodes them richly, storing abundant neural information that later makes the memory seem expansive. In contrast, routine and familiar experiences compress, appearing shorter because they require less cognitive processing. This paradox, the gap between physical time and the time of lived experience, is at the heart of our exploration. Time, as described by classical physics, is a constant, and even flow unaffected by who observes it. Yet our personal experience of time is deeply malleable, shaped by countless factors both internal and external. It is not merely an illusion, but a phenomenon grounded in real neural and psychological processes. Studies using functional magnetic resonance imaging and electroencephalography have revealed that regions such as the supplementary motor area, the basal ganglia, and the insular cortex are intimately involved in processing temporal information. These neural circuits allow the brain to integrate sensory input, memory traces, and emotional signals, constructing a subjective sense of continuity that guides our actions and judgments. Even more intriguing is the role of attention in this process. When we focus intently on a task, our perception of time can compress, a phenomenon often referred to as a flow state. Conversely, when we are bored or anxious, each second can feel impossibly long, dragging as though it were caught in molasses. Cognitive models like those developed by Daniel Zakai and Mark Bloch suggest that the brain uses an internal pacemaker, a sort of mental metronome to estimate elapsed time. This pacemaker emits regular pulses, which are counted and interpreted by higher-order neural networks. When attention is diverted or the pace of external events fluctuates, the counting process changes, and subjective time is stretched or compressed accordingly. It is worth pausing for a moment to marvel at the interplay between our internal clocks and the universe beyond. The universe itself is full of precise temporal measurements, from the regularity of pulsars emitting pulses every few milliseconds to the rotation of planets around their stars over hundreds of thousands of years. Astronomers at organizations such as the European Space Agency and the National Aeronautics and Space Administration rely on these rhythms to synchronize satellites, explore distant worlds, and navigate spacecraft with astonishing precision. Yet within our minds, time is far more fluid, bending and stretching in ways that defy mechanical regularity. This duality, The rigid flow of time measured by physics and the pliable stream felt by consciousness creates a gentle tension that is both puzzling and beautiful. It encourages us to reflect not only on the universe, but also on the intimate, personal lens through which we experience every instant. Time, in this sense, becomes a mirror, reflecting both the external order of the cosmos and the internal workings of our minds. Each tick of a clock, each heartbeat, each breath offers a passage through a landscape that is objective and subjective simultaneously, revealing layers of reality that coexist yet do not always align. As we settle into this exploration, allow yourself to feel the elasticity of your own temporal experience. Notice how moments may stretch or contract as you attend to your thoughts, your surroundings, or even the gentle cadence of my voice. The paradox of time is not something to resolve quickly or to grasp in a single understanding. Rather, it is a space for reflection, a lens through which we can appreciate the complexity of experience. By observing the subtle differences between measured time and felt time, we gain insight into both the architecture of the universe and the inner workings of consciousness. The path ahead will carry us through physics, neuroscience, psychology, and philosophy, each layer adding depth and perspective to the question, why does time not flow the way it feels? And so, we begin this journey calmly, allowing the mind to float alongside the seconds that tick externally, while expanding or contracting according to the rhythms of attention, memory, and sensation within. In doing so, we approach the profound and often playful mystery of temporal perception, the quiet wonder of living within a stream that is both measured and felt, constant and fluid, familiar and endlessly surprising. Long before the strange and flexible nature of time was discovered, scientists conceived of it as absolute, steady, and unchanging. Isaac Newton, writing in the 17th century, described time as absolute, true, and mathematical, flowing equably without regard to anything external. In this view, each second ticked with perfect uniformity, independent of motion, matter, or observation. Newton's perspective offered a framework for understanding motion and gravity that was remarkably successful for centuries. Combined with Pierre-Simon Laplace's deterministic vision, the idea emerged that if one knew the precise positions and velocities of every particle in the universe, one could, in principle, predict the entire future and reconstruct the past. Time, in this classical view, was a perfectly straight line, marching forward in unwavering increments, as reliable as the swing of a pendulum or the orbit of the Earth around the Sun. This notion of linear, uniform, deterministic time formed the backbone of physics for centuries, and it is easy to see why. It allowed humans to map the heavens, predict eclipses, and navigate the seas with astonishing precision. Yet, it is also an abstraction that does not fully reflect the universe we inhabit. For even in Newton's era, philosophers such as Gottfried Wilhelm Leibniz argue that time might be relational, dependent on the ordering of events rather than a flowing entity in itself. These debates foreshadowed the dramatic transformations that would arrive in the early 20th century, when Albert Einstein challenged the assumption of universal, absolute time. Einstein's theory of special relativity, published in 1905, revealed that time is not constant across all observers. When objects move at speeds approaching the speed of light, time itself stretches and contracts. A clock moving rapidly relative to an observer will tick more slowly than one at rest, a phenomenon known as time dilation. Just a few years later, in 1907, general relativity expanded this framework by showing that time is also affected by gravity. Massive objects like planets or stars warp the very fabric of space-time around them, and clocks situated closer to these objects tick more slowly compared to those further away. Space and time are intertwined, forming a four-dimensional continuum in which motion and gravity directly influence the passage of moments. These insights, revolutionary at the time, were confirmed by meticulous experiments. In 1971, Joseph Herfel and Richard Keating, physicists at the United States Naval Observatory, conducted a daring test. They flew highly precise atomic clocks around the world on commercial airliners, both eastward and westward, and compared them with identical clocks remaining on the ground. The results were astonishing, yet consistent with Einstein's predictions. The airborne clocks measured time differently, moving slightly faster or slower, depending on their direction and velocity. The discrepancies were on the order of nanoseconds, tiny fractions of a second, yet perfectly measurable. This experiment, though less famous than the theoretical equations, remains a concrete demonstration that time is not the same for everyone, and that our intuitive sense of it is incomplete. To understand this more deeply, imagine travelling near the speed of light, almost 300,000 kilometers per second. A journey lasting only a few hours aboard such a vessel could result in years passing on Earth. This is not science fiction, but a direct consequence of Einsteinian physics. Similarly, in the presence of a supermassive black hole, time near the event horizon flows far more slowly than it does for a distant observer. Astronomers and physicists have used these principles to calculate the orbits of stars around Sagittarius A star, the supermassive black hole at the centre of the Milky Way, confirming that relativistic time effects are essential for accurate predictions. Human intuition, of course, struggles with these scales. Our minds evolved to perceive time on the scale of seconds, minutes, and hours, and to anticipate future events over days, months, and perhaps years. We are not naturally equipped to feel the subtle stretching of milliseconds caused by high velocities or intense gravity. Yet in our everyday lives, echoes of these effects appear more subtly. For example, when astronauts spend months aboard the International Space Station, experiencing slightly less time passage relative to those on Earth, they are living a small-scale manifestation of relativistic effects. Even in this familiar context, time feels constant to those experiencing it, while objective measurements reveal slight deviations. The equations of relativity, though elegant, can also be expressed simply in words for clarity. In special relativity, the time experienced by a moving observer, which we can call prime, relates to the time measured by a stationary observer, t, according to the formula t prime equals t divided by the square root of 1 minus v squared over c squared, where v is the relative velocity and c is the speed of light. This relationship shows that as velocity approaches the cosmic speed limit, time for the moving observer slows dramatically relative to the stationary frame. It is an equation that humbles the imagination, showing that time is not universal, but conditional upon movement and perspective. General relativity adds a further dimension. Time is affected by gravity, with stronger gravitational fields slowing clocks compared to weaker fields. In a simple example, a clock placed at sea level ticks slightly more slowly than a clock atop a mountain, because it experiences a stronger gravitational pull from Earth's mass. Engineers designing the global positioning system must correct for these minute differences. Without accounting for relativistic effects, GPS locations would drift by kilometers every day. This is a remarkable example of how theoretical physics, often considered abstract, directly intersects with human life and technology. Understanding time in this flexible, observer-dependent way begins to bridge the gap between physics and experience. While seconds on a wristwatch may feel steady, the universe has other plans, revealing that time is a property not of the universe alone, but of the universe in relation to those observing it. Human perception of the passage of moments is inevitably filtered through biology and cognition, which means that our felt experience is just one layer atop the deeper, more complex fabric of space-time. Our internal clocks, built from neural oscillators and biochemical rhythms, do not tick at the same rate as the cosmic or atomic clocks that measure the universe itself, yet they give meaning and structure to our lives. It is a gentle reminder that time is not only what is measured but also what is experienced, a living phenomenon that bends, stretches, and interacts with everything around it. As we continue to explore the mysteries of temporal perception, we will see how the laws of physics provide a foundation, while the mind interprets, filters, and sometimes even playfully reshapes the seconds, minutes, and hours we call our lives. In this way, we come to appreciate that time, far from being a simple, uniform river, is a rich and textured landscape, simultaneously external and deeply personal, waiting for our attention to reveal its many subtleties. Beyond the scales of human experience, time unfolds on a cosmic stage, vast and nearly incomprehensible in its sweep. To measure it, astronomers rely on the remnants of the earliest moments of the universe, encoded in the cosmic microwave background radiation, a faint glow that fills every corner of the sky. Discovered in 1965 by Arno Penzias and Robert Wilson at Bell Laboratories, this radiation provides a universal timestamp, a frozen snapshot of the cosmos roughly 380,000 years after the Big Bang. By studying its uniformity and subtle fluctuations, Scientists can determine the age of the universe with remarkable precision, currently estimated at about 13,800,000,000 years. In this way, the cosmos itself keeps a clock, one that dwarfs the fleeting minutes and hours of our own lives. But cosmic time is not merely about counting seconds or years. It is intimately linked to the concept of entropy, the measure of disorder in a system which Ludwig Boltzmann first connected to the directionality of events in the 19th century. Entropy provides what physicists call the thermodynamic arrow of time, a principle explaining why we remember the past but cannot recall the future. Sean Carroll, a contemporary theoretical physicist at the California Institute of Technology, has expanded on this idea, showing that as the universe expands, entropy tends to increase, giving time its unmistakable forward momentum. Each event adds to the cumulative disorder, establishing a direction from the highly ordered early universe toward a progressively more entropic future. It is a simple principle on the surface, but profound in implication. Time, as we perceive it, flows because disorder increases, and without this increase, our familiar sense of cause and effect would vanish. The physicist and philosopher Julian Barber offers another perspective, one that challenges conventional assumptions. He suggests that time does not exist independently, flowing uniformly across the cosmos. Instead, time emerges from change itself. According to Barber, the universe is a series of configurations, and what we call the passage of time is simply the sequence of differences between one configuration and the next. In other words, time is a measure of the order and change in the universe, not an entity that exists apart from events. In this view, time is stitched into the fabric of reality through motion, transformation, and the relationships between objects. Moments gain significance not because they tick on a universal clock, but because they represent changes in the state of the cosmos. Understanding these principles casts human experience in a new light. The universe operates on scales that dwarf our comprehension, from galaxies spinning over hundreds of millions of years to clusters of stars coalescing and dispersing across billions of years. Cosmic time is measured in epochs, eons, and billions of years, yet our subjective experience compresses these vast stretches into a few lifetimes. When we contemplate a single star's journey from formation to supernova, we might try to grasp the immensity, but our minds inevitably collapse millennia into moments. The contrast between our perception and the temporal expanse of the universe emphasizes both our smallness and the richness of the cosmos surrounding us. Astronomers and cosmologists continue to probe these scales with ever greater precision. Research groups at the European Space Agency, NASA's Goddard Space Flight Center, and institutions such as the Kavli Institute for Cosmology in Cambridge use data from satellites like Planck and the Wilkinson Microwave Anisotropy Probe to refine our understanding of cosmic expansion, matter distribution, and the early universe. Observations of distant supernova, quasars, and gravitational lensing help chart the universe's growth, providing benchmarks for the flow of cosmic time. Each measurement, each new piece of data, enriches our conception of how time is woven into the structure of reality. The interplay of entropy and expansion also offers insights into the nature of the universe's beginning. In the earliest fractions of a second after the Big Bang, energy densities were unimaginably high, and matter existed in forms unlike anything we encounter today. As the universe expanded, energy cooled, particles combined, and structures began to emerge, creating the tapestry of stars, galaxies, and planets we observe. This unfolding was not random. It followed physical laws and probabilistic tendencies that guide the universe from order to ever greater disorder. The accumulation of these changes, over billions of years, constitutes the cosmic narrative in which our own fleeting lives are embedded. Every heartbeat, every passing minute, is set against this immense backdrop, a microcosm of the universe's relentless forward movement. Even with the vastness of these scales, certain physical principles provide consistent markers. The rotation of pulsars, neutron stars spinning with incredible regularity, allows astronomers to measure intervals with precision rivaling atomic clocks. Similarly, the oscillation of light from distant quasars and the gravitational interactions among galactic clusters provide additional means of synchronizing our cosmic understanding. These natural phenomena, measured in years, decades, or centuries, offer reference points that make the intangible vastness of cosmic time more concrete. They remind us that while our perception of time may be elastic and subjective, the universe maintains an underlying rhythm that we can observe, quantify, and begin to comprehend. Reflecting on these cosmic scales inevitably reshapes our perspective on everyday time. The day-to-day seconds that seem to stretch or collapse, the fleeting hours of joy, and the long stretches of anticipation all occur within a universe that has been evolving for billions of years. This juxtaposition can be both humbling and inspiring. It reveals that the subjective elasticity we experience, moments that linger or vanish, is but a subtle echo of a universe governed by both order and the inexorable increase of entropy. Time, in this cosmic sense, is both a universal property and a deeply personal experience, linking our internal consciousness to the grand narrative of the cosmos. The study of cosmic time, entropy, and change also invites philosophical reflection. If time emerges from the sequence of changes as Julian Barber proposes, then every instant we experience carries significance as part of an ongoing pattern. Moments are defined not by a universal metronome but by relationships, motion, and transformation. This resonates with our own lived experience, where each action, thought, or memory is a change that gives structure to the flow of our lives. In this light, observing the universe is not merely a scientific exercise. It is an invitation to notice the subtle, interconnected patterns that allow time to exist, both as a measurable quantity and as the felt rhythm of our consciousness. And so, as we drift through the stars, galaxies, and cosmic microwave background, we begin to sense the duality of time, precise and measurable across the universe, yet elastic and intimate within the human mind. The arrow of time, guided by entropy and expansion, propels the cosmos forward, while our perception bends, stretches, and occasionally halts in response to attention, memory, and emotion. By observing these interactions, we gain a richer understanding of the universe and our place within it, appreciating that the flow of time is neither simple nor uniform, but a layered and intricate tapestry, spanning from the microscopic pulses of particles to the sweeping expansion of the cosmos itself. Within the human body, time operates on scales vastly different from the cosmic or relativistic measurements explored by physicists. Here, time is deeply biological, regulated by complex networks of biological clocks that orchestrate rhythms from milliseconds to months. At the center of this system lies the suprachiasmatic nucleus, or SCN, a tiny cluster of neurons in the hypothalamus that acts as the master pacemaker, coordinating circadian rhythms that follow roughly 24-hour cycles. These rhythms govern sleep-wake patterns, body temperature, hormone release, and many other physiological processes, aligning the body with the environmental day-night cycle. The SCN receives input directly from the retina, allowing light to act as a synchronizing signal, keeping our internal clocks attuned to the rotation of the Earth. Beyond the central pacemaker, cells throughout the body maintain their own oscillatory rhythms. These cellular oscillators, found in organs such as the liver, heart, and lungs, communicate with the SCN through chemical signals and neuronal pathways. Collectively, they form a hierarchy of timing mechanisms where systemic rhythms integrate with local oscillators to produce coherent physiological cycles. These rhythms are not static. They interact dynamically with external cues and internal states, creating the fluid temporal experience that we inhabit. Disruption of these systems can lead to jet lag, fatigue, or cognitive impairment, revealing how finely tuned our sense of biological time truly is. Chronobiologists like Till Roeneberg, based at Ludwig Maximilian University in Munich, have explored the consequences of these rhythms on daily life, particularly the phenomenon he terms social jet lag. This occurs when individuals' internal clocks are misaligned with societal schedules, such as early school or work start times. Roeneberg's research shows that chronic misalignment between biological and social time can impact mood, cognition, and even metabolic health, emphasizing that our perception of time is inseparable from our physiology. The elasticity of subjective time, the way moments seem longer or shorter, often reflects the state of these internal rhythms. A well-synchronized body may perceive time more fluidly and efficiently, while misalignment can make hours feel sluggish or disjointed. Hormones play a pivotal role in regulating these rhythms. Melatonin, produced by the pineal gland in response to darkness, signals the onset of sleep and prepares the body for restorative cycles. Its release is tightly coupled to the SCN, providing a biochemical marker of night. Conversely, cortisol, secreted by the adrenal glands in the early morning, promotes wakefulness and alertness. The ebb and flow of these hormones across a 24-hour cycle shape not only sleep patterns, but also the perception of temporal flow. Moments of high alertness can seem to pass quickly, while fatigue can elongate our sense of duration, reflecting a biological interpretation of time that operates beneath conscious awareness. Experimental evidence from space agencies further illustrates the adaptability and sensitivity of these clocks. Astronauts aboard the International Space Station experience an environment where the sun rises and sets approximately every 90 minutes. NASA and the European Space Agency have documented how circadian rhythms become desynchronized in such conditions, requiring the use of carefully timed light exposure and activity schedules to maintain sleep and cognitive function. These findings highlight the plasticity of the human circadian system, capable of adapting to radically different temporal environments, yet also revealing the discomfort and cognitive strain that arise when natural rhythms are disrupted. It underscores that subjective time is inseparable from the functioning of these biological systems. Ultradian and infradian rhythms add additional layers to our temporal architecture. Ultradian rhythms, cycling on scales of minutes to hours, govern processes such as heart rate variability, hormone pulses, and stages of sleep including rapid eye movement and slow-wave sleep. Infradian rhythms, with cycles longer than a day, influence menstrual cycles, seasonal mood variations, and migratory behaviors in some animals. Together, these nested cycles create a temporal framework that is multi-scaled, dynamic, and interdependent. They illustrate that human experience of time is not linear in the strict Newtonian sense, but composed of overlapping rhythms that may accelerate or decelerate subjective perception, depending on alignment and internal coherence. The interaction of these rhythms with attention and cognition further shapes perceived duration. When internal clocks are in sync and cognitive resources are fully engaged, events may feel compressed, passing almost unnoticed. Conversely, when rhythms are disrupted, as in social jet lag or travel across time zones, subjective time may stretch, with moments feeling elongated or fragmented. Neuroimaging studies reveal that networks in the prefrontal cortex and the basal ganglia integrate signals from circadian systems with attention and memory networks, forming the neural substrate of time perception. This integration allows humans to navigate complex temporal environments, linking physiological rhythms to conscious experience. Furthermore, the circadian system interacts intimately with environmental cues beyond light, including social interactions, temperature fluctuations, and feeding schedules. These Zeitgebers, or time givers, provide external reference points that help calibrate our internal clocks. In the absence of consistent cues, rhythms may drift, a phenomenon observed in both laboratory studies and long-term space missions. Such drift illustrates that while biological clocks are remarkably self-sustaining, they remain sensitive to context, reinforcing that our experience of time is a negotiation between internal mechanisms and the world around us. Ultimately, understanding biological clocks reveals that the elasticity of subjective time is deeply grounded in physiology. The SCN orchestrates cellular oscillators adjust locally, hormones provide chemical timing cues, and cognitive networks interpret these signals, producing the rich, fluid sense of temporal flow we inhabit. From daily routines to the extraordinary environment of space, these systems illustrate that our perception of time is not fixed, but a living interplay between body, brain, and environment. Every pulse, hormone surge, and neural oscillation contributes to the subjective experience that makes moments feel fleeting or enduring. A quietly profound reminder that time, as we live it, is intimately tied to the rhythms of life itself. Memory is a bridge between past and present, a delicate mechanism that shapes not only what we know, but how we experience the passage of time. Within the brain, memory exists in multiple forms, each contributing uniquely to temporal perception. Episodic memory allows us to mentally travel to specific moments in our personal history, recalling experiences with their associated sights, sounds, and emotions. It is the system that enables us to remember the first time we rode a bicycle, the warmth of sunlight on a summer afternoon, or the precise sequence of events leading to a small triumph or mistake. In contrast, semantic memory encodes general knowledge about the world, facts and concepts, such as understanding that the Earth revolves around the Sun or that water freezes at 0 degrees Celsius. While semantic memory provides a stable framework for knowledge, episodic memory colors our experience of duration, contributing to the sense that some periods stretch endlessly while others vanish like shadows at dusk. Endel Tulving, a pioneering cognitive psychologist, elucidated the structure and function of episodic and semantic memory, revealing how these systems interact with our perception of time. Tulving demonstrated that episodic memory depends heavily on the context of the event, integrating temporal, spatial, and emotional cues to reconstruct the flow of experience. Mark Wittmann, whose work in cognitive neuroscience builds upon these foundations, explores how the brain's timing mechanisms are influenced by memory. He notes that the richness of encoding during an event determines how long it feels in retrospect. When the mind experiences something novel, the density of encoded information makes the interval seem longer, a phenomenon often referred to as temporal expansion. Conversely, repetition or highly predictable sequences result in fewer distinctive memory traces, compressing the subjective duration of time. This principle helps explain why childhood summers often feel endless while adult years seem to accelerate. In youth, nearly every experience is new, requiring intensive cognitive processing and extensive encoding in episodic memory. The mind attends carefully, capturing detail after detail, producing a tapestry of experiences that, when recalled, stretches the subjective timeline. As adults, life often involves repetition, routine commutes, familiar workplaces, and repeated social interactions. Our episodic memory has fewer novel points of reference, and so time appears to pass more swiftly, almost imperceptibly. Studies using prospective and retrospective timing tasks have consistently demonstrated this effect, linking memory encoding density to perceived duration. Emotional intensity further modulates this process. High arousal events, whether exhilarating or frightening, are encoded more densely and vividly, creating a lasting impression that elongates subjective time. Neurologically, the amygdala plays a critical role in enhancing memory formation during emotionally charged events, interacting with the hippocampus to preserve temporal order and contextual detail. The brain records these moments with higher fidelity, allowing them to dominate our retrospective sense of duration. In effect, our memories are not simply stored snapshots. They are actively constructed narratives that reconstruct the passage of time based on salience, novelty, and emotional content. Attention and memory work hand in hand to influence temporal perception. When attention is focused intensely on an experience, such as during problem-solving, creative activity, or acute observation, episodic encoding is enriched. Moments are registered in greater detail, providing a more expansive timeline when recalled. Conversely, when attention wanders or experiences are underprocessed, temporal compression occurs. Neuroimaging studies have revealed that regions including the prefrontal cortex, the hippocampus, and the parietal cortex are involved in integrating attention with memory to form coherent sequences of events. These sequences provide the scaffolding upon which subjective time is constructed, illustrating that our felt experience is an emergent property of multiple interacting cognitive systems. Interestingly, memory's influence on time is not limited to retrospective judgment. Prospective timing, or our anticipation of future events, also depends on stored experiences. When we predict the duration of an upcoming activity, our brain draws upon previous similar experiences, adjusting expectations based on memory. This explains why a long monotonous lecture can seem interminable if we recall past sessions as tedious, while a similar length of time engaged in stimulating or novel activity feels much shorter. Memory creates a dynamic feedback loop, constantly shaping how we perceive both past and future durations. Experiments in laboratory settings have provided additional insight. Participants exposed to sequences of novel stimuli such as unfamiliar images, sounds, or tasks consistently report subjective durations longer than those exposed to repeated familiar stimuli of the same objective length. Functional magnetic resonance imaging and electroencephalography reveal increased neural activity in regions associated with novelty detection, including the hippocampus and prefrontal cortex during these intervals. These findings illustrate the mechanistic basis for the way episodic memory density stretches subjective time, and conversely, why repetition leads to compression. The reconstruction of experience through memory also emphasizes that subjective time is not linear in the way we often assume. Moments are reassembled from the interplay of sensory input, attention, emotional salience, and prior knowledge, producing a temporal narrative that can expand, contract, or even loop back in recollection. This aligns with Wittmann's observation that time perception is fundamentally event-based, anchored to salient changes and transitions, rather than to an internal metronome alone. In this sense, our experience of time is less like a flowing river and more like a mosaic, where each tile represents a moment stored, encoded, and interpreted by memory. Ultimately, memory transforms raw temporal intervals into meaningful experience. It provides the context through which the brain interprets seconds and minutes as moments that can linger, pass unnoticed, or resonate emotionally for years to come. By understanding the roles of episodic and semantic memory, the mechanisms of encoding, and the influence of novelty and emotion, we begin to see why subjective time is so flexible, why a single day can feel infinitely long or vanish in an instant. Memory does not merely record time, it actively sculpts the temporal landscape of our lives, linking past, present, and future into the intricate, layered experience that shapes our consciousness. Attention is a quiet architect of our perception, shaping how we experience the flow of time in ways that often go unnoticed. When the mind focuses deeply on a single task or stimulus, our sense of temporal duration can compress, making hours feel like minutes. Conversely, when attention wanders or we are hyper-aware of each passing moment, time can stretch, moments dragging with a peculiar intensity. This modulation of perceived duration is not random. It arises from how the brain allocates processing resources. Cognitive neuroscientists have shown that focused attention engages networks in the prefrontal cortex, the parietal lobe, and the anterior cingulate cortex, which together monitor incoming sensory information, prioritize what is salient, and encode it with high temporal fidelity. The result is that our experience of time is intimately tied to the way attention directs cognitive effort. Temporal illusions provide striking demonstrations of this effect. One well-known phenomenon, chronostasis, occurs when the first moment after a sudden gaze shift, such as glancing at a clock or a watch, seems to last longer than it objectively does. This stopped clock illusion arises because the brain retroactively adjusts perception to maintain a continuous narrative, essentially stretching the first tick of time to align with prior sensory input. Researchers have proposed that this effect demonstrates the brain's active role in constructing a coherent timeline, filling gaps to prevent disorientation. It is a small trick of perception, yet it highlights a fundamental principle. Time is not simply received. It is continuously reconstructed by attention and expectation. Flow states, described in detail by psychologist Mihaly Csikszentmihalyi, offer another window into temporal elasticity. When an individual is fully absorbed in an engaging activity, such as playing music, painting, or solving a challenging problem, subjective time often compresses. Hours can pass unnoticed as attention is intensely focused, and the mind becomes deeply immersed in the present task. Neuroimaging studies have shown that during flow, activity in the default mode network decreases, while networks involved in task-related attention and reward are highly active. This combination facilitates a seamless integration of sensory input, motor planning, and cognitive evaluation, producing the subjective feeling that time is slipping away even while precision and skill are heightened. Dan Zakai, a leading figure in the study of temporal perception, distinguishes between prospective and retrospective timing. In prospective timing, we are aware that we are monitoring the passage of time, such as when anticipating an upcoming meeting or counting seconds. Attention is directly focused on time itself, and minor fluctuations in cognitive engagement or stimulus complexity can significantly alter perceived duration. Retrospective timing, by contrast, occurs when we estimate how long an event lasted after it has passed, relying heavily on memory and the density of encoded events. A novel, richly detailed experience may seem to last longer in retrospect, whereas monotonous or repetitive intervals can appear brief. Zakai's models help explain why attending to different aspects of experience changes the felt duration, reinforcing the connection between cognitive focus and temporal elasticity. Novelty also enhances the brain's temporal resolution. When encountering unfamiliar stimuli, whether in the form of sights, sounds, or experiences, the brain allocates additional processing power to encode details accurately. This heightened encoding results in a denser memory trace, which, when recalled, stretches the perceived length of the event. Conversely, familiar or repetitive events demand fewer neural resources and are compressed in memory. Experiments by researchers in cognitive neuroscience, using both behavioral and neuroimaging methods, have shown that novel sequences activate the hippocampus and prefrontal cortex more intensely, correlating with longer subjective duration. This demonstrates that the perceived passage of time is intricately linked to the richness of the moment and the attentional resources devoted to it. Interestingly, temporal perception is influenced not only by external novelty, but also by internal shifts in attention. Multitasking, divided attention, or rapid alternation between tasks can fragment perception, producing a disjointed sense of duration. The brain must constantly reconcile competing streams of information, integrating them into a coherent temporal narrative. When attention falters, events may appear to pass inconsistently. Some moments feel fleeting, others exaggerated. This dynamic interplay between attentional focus and cognitive integration underscores the brain's role as an active constructor of time, rather than a passive recorder. In practical terms, these principles explain many common experiences. Waiting in a crowded room with nothing to occupy the mind often feels interminable, each second stretched by heightened awareness. Conversely, engaging deeply in conversation, creativity, or play compresses subjective time, leaving us surprised when hours have passed unnoticed. The combination of attention, novelty, and cognitive load creates a flexible temporal landscape, one that adapts to the mind's engagement with the environment. Researchers such as Mark Wittmann have explored how these effects are mediated by neural oscillators in the brain, including theta and gamma rhythms, which provide an internal scaffold for temporal sequencing and perception. Ultimately, attention and novelty reveal the brain's remarkable capacity to shape experience. Time, rather than being an absolute measure, is a construct woven from the interplay of sensory input, memory, and focus. Moments are stretched or compressed. Illusions like chronostasis highlight the brain's reconstructive tendencies, and flow states demonstrate the profound influence of immersion. By attending to these mechanisms, we gain insight into why time feels so variable in our daily lives, and how our perception of duration emerges from the ongoing dialogue between mind, memory, and the world around us. In this way, cognitive focus transforms not only how we act in the present, but also how the seconds, minutes, and hours of our lives are remembered and understood. Emotions are powerful architects of our temporal experience, shaping the perception of moments in ways that can make time feel stretched, contracted, or even suspended. Arousal, fear, excitement, and stress are not merely feelings. They are physiological states that influence the neural processing of time, altering the subjective duration of events. Christoph Kornblum, a neuroscientist studying temporal perception, and sociologist Theuts have explored how emotional intensity interacts with attention and memory to modulate the sense of elapsed time. Their work reveals that moments charged with emotion are encoded more densely in the brain, producing the familiar sensation that time slows when danger approaches or excitement peaks. At the heart of this process lies the amygdala, a small almond-shaped structure deep within the temporal lobe, responsible for processing emotional salience and coordinating responses to significant stimuli. The amygdala communicates with the hippocampus to enhance memory encoding during emotionally charged events, and with the prefrontal cortex to direct attention toward critical details. Functional magnetic resonance imaging and electrophysiological studies show that heightened amygdala activity correlates with expanded perceived duration, confirming that emotion is not just an accompaniment to experience, but a direct influencer of temporal perception. The biochemical mechanisms underlying this influence are equally significant. During moments of stress, fear, or exhilaration, the body releases adrenaline, also called epinephrine, and norepinephrine, catecholamines that increase heart rate, blood pressure, and sensory alertness. These chemical messengers enhance the salience of incoming stimuli, heightening attention and accelerating neural firing rates. In practical terms, this means that during a high-stakes event, such as narrowly avoiding an accident or witnessing a breathtaking scene, the brain processes more information per unit of objective time. As a result, when recalling these events, each second feels longer, giving the impression that time itself has slowed. Research in both laboratory and naturalistic settings supports this effect. Participants exposed to sudden loud noises, unexpected threats, or visually intense stimuli consistently report subjective temporal expansion. Neurophysiological recordings reveal simultaneous increases in amygdala and hippocampal activity, along with modulation of cortical networks responsible for attention and executive function. These findings illustrate a tight interplay between emotional arousal, memory encoding, and attentional focus. As emotion intensifies, temporal resolution becomes finer, and the subjective experience of each moment is amplified. In this way, the brain constructs a richer, more detailed representation of emotionally significant events, making them appear elongated in memory. Emotionally charged time perception is not uniform across individuals or contexts. Personality traits, prior experiences, and baseline anxiety levels all modulate the degree to which moments expand or contract under arousal. Some people are more sensitive to threats, with stronger amygdala reactivity, leading to more pronounced temporal dilation during fear-inducing events. Others may experience similar stimuli with less intensity, producing only modest changes in perceived duration. Studies employing both behavioral measures and neuroimaging have revealed these individual differences, highlighting the complex interaction between physiology, psychology, and perception. The concept of temporal dilation during intense moments also has practical implications for daily life and survival. From an evolutionary perspective, heightened awareness and detailed encoding of threatening or important events confer advantages in learning, memory, and decision-making. By expanding subjective time, the brain allows more precise perception and reaction, improving the chances of navigating danger successfully. Even outside life-threatening contexts, this mechanism explains why emotionally significant experiences, whether joyous celebrations, heartbreaks, or creative breakthroughs, linger vividly in memory long after the moment has passed. In addition to acute events, sustained emotional states can shape the perception over longer intervals. Chronic stress or ongoing excitement modulates baseline arousal levels, influencing how daily experiences are perceived. The release of cortisol, a glucocorticoid hormone associated with long-term stress, interacts with the hippocampus and prefrontal cortex, subtly altering the brain's ability to encode temporal sequences. These neurochemical effects demonstrate that emotion and time perception are interdependent across both brief and extended periods, weaving together subjective experience in ways that are both immediate and cumulative. Emotion also interacts with attention to influence time perception. When arousal directs attention narrowly toward a salient stimulus, other environmental cues may fade into the background, compressing non-essential experiences while stretching the focus of critical events. This selective allocation of cognitive resources allows the brain to prioritize information most relevant to survival or well-being, reinforcing the intimate connection between emotion, attention, and the subjective elasticity of time. In essence, emotional states act as modulators of cognitive processing speed and resolution, giving each significant moment the depth and texture we intuitively feel. Experiments involving virtual reality, immersive simulations, and controlled laboratory tasks provide further evidence of emotion-driven temporal modulation. Participants navigating simulated danger zones, such as virtual heights or sudden obstacles, consistently report slowed time, while electroencephalography recordings show increased oscillatory activity in the theta and gamma bands within the amygdala-hippocampal prefrontal network. This neural activity aligns with the enhanced encoding of detail and the heightened sense of duration, demonstrating that subjective temporal dilation is not simply a perceptual quirk, but a measurable phenomenon with identifiable physiological correlates. In the end, the elasticity of time under emotional influence illustrates a fundamental principle. Perception is not passive. The brain does not merely observe the passage of seconds. It actively constructs temporal experience, integrating sensory input, memory encoding, attentional focus, and emotional salience into a cohesive narrative. Moments of fear, excitement, or intense focus appear to stretch because our neural systems are working harder, encoding more information and heightening awareness. This interplay explains why a near miss can feel to a person as if it lasted several seconds, while ordinary intervals slip by unnoticed. Time, in this sense, is as much a product of our inner landscape as it is of external measurement, highlighting the deeply personal and profoundly adaptable nature of temporal experience. At the smallest scales of reality, the familiar flow of time begins to unravel. In the quantum realm, particles exist in states that defy classical intuition, inhabiting superpositions where multiple possibilities coexist, until an observation collapses them into a definite outcome. Electrons, photons, and other quantum entities do not trace a single, well-defined path, but instead explore a landscape of probabilities, a behavior that challenges the conventional idea of a linear uniform time. Adding further intrigue, entanglement links particles across vast distances, so that the state of one instantaneously influences the state of another, seemingly defying classical temporal constraints. In this domain, time is no longer a passive backdrop. It becomes deeply dependent on the observer, entangled with the act of measurement itself. Physicists such as Carlo Rovelli, developing relational quantum mechanics, propose that time is not a universal quantity, but arises from interactions between systems. In this view, the temporal ordering of events is relative. Two observers interacting with a system may experience the sequence of occurrences differently. Rovelli emphasizes that at the fundamental level, the universe is a network of relations, and time is a property that emerges from these relationships rather than existing independently. Julian Barber takes an even more radical perspective in his concept of timeless physics, suggesting that time is not a fundamental dimension at all. Instead, the universe consists of a series of configurations, or nows, and what we perceive as the passage of time is simply the comparison between one configuration and the next. In this framework, change itself creates the impression of time, and the flow we experience is an emergent phenomenon rather than a fundamental aspect of reality. One of the most striking mathematical formulations capturing the strangeness of quantum time is the Wheeler-DeWitt equation, a central equation in canonical quantum gravity. This equation describes the quantum state of the entire universe, and, remarkably, it contains no explicit time variable. In essence, the Wheeler-DeWitt equation treats the universe as timeless, a static wave function encompassing all possible configurations. This challenges classical physics, which assumes that time is a necessary parameter for dynamics. Reconciling this timeless description with the apparent passage of time at larger scales remains one of the most profound puzzles in theoretical physics, inspiring decades of research in quantum cosmology, loop quantum gravity, and string theory. Thought experiments help illuminate the counterintuitive implications of quantum time. Consider a hypothetical universe where only two particles exist. Without interactions or measurements, these particles exist in a superposed state of all possible positions. Time, as an independent flowing quantity, has no operational meaning here. Only when a change occurs, one particle moving relative to the other, a measurement being made, does a notion of sequence and temporal order emerge. This illustrates Barber's assertion that time is relational, arising locally from change rather than being an external, universal river that carries events forward. It is a perspective that forces us to reconsider the idea that seconds, minutes, and hours are inherent to reality, rather than constructs that arise from observation and interaction. Quantum indeterminacy further complicates temporal perception. In experiments such as the famous double-slit setup, particles appear to choose paths probabilistically until measured, and the results cannot be predicted with certainty, only with probabilities. The implications for time are profound. If events at the smallest scales do not follow a deterministic sequence, then the linear progression of cause and effect, which forms the backbone of our classical understanding, is not fundamental. The universe at the quantum level is more like a web of interrelated possibilities, where the precise order of events depends on context, interaction, and observation. The indeterminacy inherent in this framework parallels the elasticity of subjective experience, where perception and attention shape how moments unfold, sometimes stretching or contracting time in the mind's eye. Experimental investigations in quantum mechanics provide concrete evidence of these effects. Quantum entanglement experiments, such as those performed by Alan Aspect in 1982, demonstrate that particles separated by meters, or even kilometers, exhibit correlations that are instantaneous within the limits of measurement. The notion of simultaneity becomes context-dependent, and the concept of a universal clock becomes inadequate. Furthermore, studies of weak measurements and delayed choice experiments reveal that the act of observation can influence not only the outcome of quantum events, but also their apparent temporal ordering. These findings underscore the non-classical nature of time in the quantum domain and suggest that our everyday intuition is deeply mismatched with the mechanics of the subatomic world. The connection between quantum mechanics and subjective perception is subtle, but intriguing. While our brains operate at scales vastly larger than their individual particles, some theorists propose that the probabilistic and relational nature of quantum events may offer a metaphorical explanation for certain temporal anomalies in consciousness. Moments of uncertainty, anticipation, or intense focus can feel stretched or suspended, reflecting a kind of psychological parallel to the indeterminacy of the quantum realm. Neuroscientists like Mark Wittmann have observed that attention, arousal, and neural oscillations can produce temporal distortions similar in character to the probabilistic, non-linear behavior of quantum events, even if the underlying mechanisms are distinct. In both cases, the flow of time is not a fixed property, but a constructed context-dependent experience. Time emerging locally from change also invites philosophical reflection. If the universe is fundamentally timeless, and the flow of seconds and hours arises from relational differences, then the everyday continuity we perceive is a product of observation and interaction rather than an intrinsic property of reality. This perspective aligns with certain interpretations of loop quantum gravity, where space-time itself is composed of discrete units, and the smooth passage of time is an emergent approximation valid only at macroscopic scales. It is a universe in which moments exist as snapshots of relational configurations, and the familiar river of time is a cognitive lens through which we interpret these changes. In practical terms, the lessons of quantum time challenge our assumptions about permanence, causality, and temporal order. They encourage us to embrace uncertainty, to recognize that the linear narrative we impose on experience is a construction rather than a universal truth. The brain, in concert with attention, memory, and emotion, constructs temporal flow in ways that echo the relational and probabilistic structures found in the quantum world. Just as particles exist in superposition until observed, moments in our own consciousness can feel fluid and malleable, expanding or contracting according to focus, novelty, and emotional salience. Ultimately, exploring quantum time reveals that the fabric of reality is not a continuous, unbroken stream. Instead, it's a mosaic of possibilities, relationships, and emergent patterns. Time at this scale is both fragile and flexible, dependent on change, observation, and interaction, rather than a fixed universal river. By contemplating these principles, we gain not only a deeper understanding of physics, but also a richer appreciation for the fluidity of our own temporal experience, recognizing that the seconds, minutes, and hours we inhabit are part of a layered, complex universe where certainty is rare and the possibilities are endless. One of the most profound insights into the nature of time comes not from clocks or calendars, but from the principle of entropy, the measure of disorder in a system. In the 19th century, Ludwig Boltzmann formalized the connection between entropy and the arrow of time, demonstrating that in an isolated system, the number of possible microscopic configurations tends to increase. This inexorable growth of disorder gives time its unmistakable directionality, explaining why we remember the past but cannot experience the future, why eggs break but never spontaneously reassemble, and why a cup of hot coffee cools on the table rather than heating itself. Entropy is, in essence, the cosmic clock that marks the progression of events, from the orderly arrangement of particles after the Big Bang to the messy, complex universe we inhabit today. Contemporary thinkers like Seth Lloyd, a physicist at the Massachusetts Institute of Technology, have extended this idea by framing time in terms of information theory. In Lloyd's perspective, the universe is fundamentally a computational system, and the passage of time corresponds to the processing and dissemination of information. Each interaction, each change of state, generates new information and increases entropy, tying the arrow of time to both thermodynamics and the logical structure of reality. In this sense, time is not merely a measure of change, but a reflection of the accumulation and transformation of information across the universe. It is a perspective that links the macroscopic sweep of stars and galaxies to the microscopic decisions of particles, uniting physics, computation, and information in a single conceptual framework. Yet the notion of time's direction is not without paradox. Loschmidt's paradox, formulated by Johann Loschmidt in the 19th century, challenges the idea that entropy should always increase. On a microscopic level, the laws of physics are nearly time-symmetric. the equations governing particle motion work just as well backward as forward. In principle, if we reversed all particle velocities in a system, the system would retrace its steps, reducing entropy and reversing time's arrow. However, at macroscopic scales, such precise reversal is impossible, and the sheer number of particles involved ensures that entropy increases overwhelmingly in the forward direction. This distinction between micro-reversibility and macro-reversibility reconciles the apparent symmetry of physical laws with our lived experience of time moving inexorably forward. The implications of entropy extend into the workings of the brain and the perception of time itself. Neural networks, memory formation, and attentional processes are governed by physical interactions among neurons, each following principles consistent with thermodynamics. As the brain encodes experiences, information is processed and consolidated, a process inherently linked to entropy increase. High-resolution fMRI studies reveal that moments of novelty, heightened attention, or emotional intensity produce dense patterns of neural activation, which are then integrated into coherent memory traces. In effect, the subjective arrow of time, the way moments are felt and recalled, is mirrored in the thermodynamic processes that govern neural activity, suggesting a deep link between cosmic and psychological temporality. Entropy also interacts with quantum phenomena, providing a bridge between classical macroscopic time and the probabilistic, observer-dependent time of the subatomic world. In quantum mechanics, individual particles can exist in superpositions with potential outcomes encoded as probabilities. The act of observation collapses these possibilities into specific outcomes, increasing information and, in turn, contributing to entropy growth. This connects the seemingly timeless quantum domain with the macroscopic flow of time experienced by observers, showing that the arrow of time emerges across scales, from subatomic particles to galaxies. It is a remarkable illustration that time, far from being a simple or uniform quantity, is an emergent feature arising from both physical laws and informational processes. The concept of information-theoretic entropy also has practical and philosophical implications. In computational systems, each logical operation generates minimal amounts of entropy, a principle described by Rolf Landauer in 1961, known as Landauer's principle. When applied to the universe as a whole, it reinforces the idea that time's arrow is linked to the generation and transformation of information. Every physical process, whether the movement of a star, the firing of a neuron, or the unfolding of a chemical reaction, contributes to this flow of information, embedding the passage of time in the fabric of reality. Understanding time through this lens reveals that the directionality we perceive is not arbitrary, but a consequence of fundamental principles governing both matter and knowledge. Observations at cosmic scales further illustrate the interplay of entropy and time. As galaxies evolve, stars burn through fuel, and black holes grow, the universe moves towards states of higher disorder. The second law of thermodynamics dictates that the total entropy of the universe increases, providing a large-scale arrow of time that aligns with our intuitive experience. Causes precede effects, and processes unfold from order to disorder. Even in regions of local decrease in entropy, such as during star formation or the emergence of life, the net effect on the surrounding system ensures that total entropy rises. In this way, the universe orchestrates a consistent forward movement that governs both cosmic events and the subtle experiences of time in conscious beings. Integrating entropy, information, and temporal perception highlights the multifaceted nature of time's arrow, from the deterministic laws of Newtonian physics to the relativistic distortions of Einstein, from the probabilistic behavior of quantum particles to the informational structure of the cosmos. A pattern emerges. Time's direction is defined by change, disorder, and the accumulation of knowledge. Psychological studies, cosmological observations, and theoretical physics converge to show that the same principle underlies phenomena as diverse as neural processing, memory encoding, stellar evolution, and the expansion of the universe itself. Each moment, each tick of the clock, represents not just the passage of seconds, but the unfolding of information, the progression of entropy, and the forward march of events that structure reality. This perspective also deepens our understanding of subjective experience. When attention is focused and memory is enriched, events feel longer and more vivid, a reflection of the local increase in informational content within the brain. When experiences are routine or minimally attended to, subjective time compresses, echoing the principle that lower information density corresponds to faster perceived passage. By linking thermodynamics, information theory, and cognitive neuroscience, we see that our felt experience of time is an emergent property of physical laws and neural processing, intimately connected to the fundamental structure of reality. Ultimately, entropy is both a cosmic and a personal guide. It defines the arrow along which the universe unfolds, informs the internal rhythms of our minds, and provides a unifying principle connecting quantum uncertainty, macroscopic processes, and cognitive perception. From the earliest moments after the Big Bang to the dense pattern of neural firings in a single human brain, the increase of disorder and the flow of information ensure that time has direction, that moments have order, and that the passage of experience is inseparable from the unfolding of the universe itself. Through this lens, we can appreciate time as an intricate tapestry woven from matter, energy, information, and consciousness. A forward-moving thread that connects everything from the smallest particle to the vast expanse of galaxies, and to our own fleeting, remarkable perception of the world. Across human history, cultures have constructed time in ways that reflect both practical necessity and philosophical perspective. Some societies perceive time as linear, a sequential progression from past through present to future. This conception, prominent in Western thought, emphasizes causality, deadlines, and forward planning, with events unfolding like the links of a chain. Other civilizations embrace cyclical time, viewing existence as repeating patterns of seasons, celestial movements, and generational cycles. Ancient Mayan and Hindu traditions, for instance, conceived of time as a series of repeating epochs, where the rise and fall of worlds and societies followed eternal rhythms. In such frameworks, events are less about irreversible progression and more about recurrence, shaping how individuals experience and value the passage of moments. Anthropologists and cross-cultural psychologists have observed that these differences influence the perception of temporal duration and urgency. Societies classified as monochronic, often found in Northern Europe and North America, tend to organize life around fixed schedules, valuing punctuality and the linear progression of tasks. Time is compartmentalized into discrete units, and interruptions are generally unwelcome. By contrast, polychronic societies, common in parts of Latin America, Africa, and the Middle East, treat time as flexible, emphasizing relationships over schedules and allowing multiple activities to occur simultaneously. In polychronic contexts, events are experienced more fluidly, and the subjective passage of time often feels slower or more malleable because priorities are relational rather than strictly sequential. The technological instruments humans have created to measure time have also profoundly shaped perception. The invention of mechanical clocks in the 14th century allowed precise measurement of hours and minutes, reinforcing linear concepts and establishing schedules that synchronize labor, prayer, and commerce. By the 18th and 19th centuries, industrialization intensified this effect, with factory bells and work shifts creating rigid temporal frameworks that conditioned attention and behavior. In the 20th century, the advent of digital clocks, wristwatches, and electronic timers further cemented the division of time into discrete, measurable units. Contemporary devices such as smartphones with constant notifications and reminders continuously reshape attentional patterns and the perception of temporal flow, creating what some researchers call technologically mediated time. Anthropological research adds nuance to these observations. Scholars such as Edward Hall and Robert Levine have explored how different cultures structure daily life, revealing substantial variability in the experience of temporal duration. In some tribal societies, the measurement of time is closely tied to environmental cycles such as sunrise, tides, or agricultural events rather than fixed hours. In these contexts, the subjective experience of minutes, hours, or days is less rigid, and cognitive systems adapt to the rhythms of nature. Observations from ethnographic studies show that the same activity can feel longer or shorter, depending on cultural frameworks, highlighting the interplay between social organization, attention, and perception. These societal constructions also influence cognition and memory. In cultures that emphasize linear scheduling and punctuality, individuals may develop attentional habits that partition experience into discrete temporal units, facilitating planning, retrospective recall, and forecasting. Conversely, in societies with flexible relational time, Attention may be distributed across multiple tasks and social interactions, producing richer, more interconnected episodic memories but a more elastic perception of duration. This demonstrates that subjective time is not merely a biological phenomenon, but also a product of cultural conditioning, social expectation, and environmental engagement. Moreover, these temporal frameworks intersect with historical developments in science and philosophy. The Enlightenment and the rise of mechanical and Newtonian physics reinforced linear, sequential conceptions of time, aligning social, technological, and scientific thought. By contrast, Eastern philosophies, including Taoism and certain strands of Buddhism, have emphasized the cyclical and interdependent nature of existence, influencing meditation practices and conceptions of causality. The interplay between cultural values, scientific understanding, and personal experience illustrates that the perception of time is shaped not only by neural mechanisms, but also by collective human frameworks, education, and philosophy. The integration of cultural and historical perspectives also sheds light on why subjective time can feel elastic in modern life. Even within highly structured societies, individuals may experience moments of temporal dilation when engaged in novel, absorbing, or emotionally intense activities. Conversely, monotonous routines imposed by industrial schedules can compress the perception of hours or days. Cognitive adaptation allows humans to navigate these frameworks, integrating internal rhythms, attentional processes, and societal expectations to maintain coherence and functionality. Psychologists have noted that individuals raised in polychronic environments often demonstrate greater flexibility in multitasking and temporal estimation, suggesting that social conditioning can modulate the brain's internal timing mechanisms. Technological change continues to influence how time is perceived and valued. The constant availability of information, social interaction, and entertainment fragments attention, producing the sensation that time is accelerating. Conversely, periods of intentional disconnection, such as retreats or meditation practices, can restore a sense of temporal expansion. This interplay between external structures, technological environments, and internal perception demonstrates that cultural constructs are not static. They interact dynamically with biology, cognition, and environment to shape our lived experience of time. Ultimately, exploring the cultural and historical constructions of time reveals that subjective experience is entwined with social frameworks, philosophical perspectives, and technological tools. Linear and cyclical views, monochronic and polychronic tendencies, and the advent of precise clocks all contribute to how humans perceive the duration and flow of events. By understanding these influences, we gain insight into the remarkable plasticity of temporal perception, recognizing that time is not merely a universal metric, but also a construct molded by collective values, attention, and adaptation. In this light, the rhythm of our daily lives is both a reflection of internal biological mechanisms and a mirror of the cultures, technologies, and philosophies that shape our shared human experience. The perception of time is rooted deeply in the architecture of the brain, distributed across multiple regions that work in concert to encode, interpret, and predict the passage of moments. At the heart of this system lies the basal ganglia, a collection of nuclei situated at the base of the forebrain, long recognized for their role in motor control but increasingly understood as central to temporal processing. The basal ganglia help generate internal signals that act as a sort of neural metronome, producing rhythmic pulses that allow the brain to estimate intervals spanning milliseconds to seconds. These pulses provide a scaffold for motor coordination, cognitive sequencing, and the anticipation of events, enabling actions to be timed precisely even in the absence of external cues. Complementing the basal ganglia, the cerebellum contributes to fine-tuned timing, particularly for sub-second intervals and the precise sequencing of movement and perception. While traditionally associated with balance and motor control, research over the past several decades has revealed the cerebellum's broader role in predicting temporal relationships, adjusting neural responses to align with anticipated events, and coordinating sensory input with motor output. In combination with cortical structures, the cerebellum enables humans to perform complex tasks requiring precise timing, such as playing musical instruments, coordinating sports movements, or engaging in rapid conversational exchange, where temporal accuracy is essential. Cortical oscillators add yet another layer to temporal perception, providing rhythmic patterns of neural activity that structure how time is encoded and integrated. These oscillations, typically in the theta, alpha, and gamma frequency bands, serve as internal clocks that synchronize neural networks across regions, allowing for coherent temporal processing. For example, theta oscillations in the hippocampus appear to track intervals during memory encoding, while gamma oscillations in the prefrontal cortex facilitate integration across distributed neural circuits. These oscillatory networks help bind sensory input, attention, and memory into a cohesive temporal narrative, creating the sense of continuity and order that we experience as the flow of time. Leading researchers such as David Eagleman, a neuroscientist at Baylor College of Medicine, have conducted extensive studies on sub-second and multi-second timing, revealing the remarkable plasticity of the brain's temporal processing. Through experiments involving rapid visual flashes, auditory sequences, and motor tasks, Eagleman demonstrated that our perception of intervals can be stretched or compressed depending on context, attention, and arousal. For instance, when participants are exposed to highly salient or surprising stimuli, their subjective experience of time expands, allowing them to encode details more densely. Mark Wittmann's work in cognitive neuroscience complements this, highlighting the interplay of emotional states, attentional focus, and neural timing mechanisms in shaping the felt passage of moments. Cortical-subcortical interactions further refine temporal perception, allowing the basal ganglia, cerebellum, and oscillatory networks to communicate effectively with higher-order cortical regions, such as the prefrontal cortex and parietal lobe. These interactions enable temporal binding, the process by which the brain integrates discrete events into a coherent sequence. Preserving the order and duration of experiences, temporal binding explains why we perceive a melody as flowing, rather than as a series of disjointed notes, and why complex motor sequences are executed smoothly, rather than in isolated, jittered steps. Neuroimaging studies reveal that disruptions to these pathways, whether through lesions or neurological conditions, can distort subjective timing, underscoring the interdependence of cortical and subcortical structures in producing coherent temporal experience. Oscillatory networks also facilitate the integration of attention, memory, and emotion. When the brain is attentive to a task or emotionally aroused, oscillations in the gamma frequency band increase, enhancing the resolution of temporal encoding. This allows for finer discrimination of short intervals and improves the precision of action timing. Conversely, during states of distraction or fatigue, oscillatory coherence diminishes, resulting in subjective time dilation or compression. Attention, memory consolidation, and emotional salience all act upon these neural rhythms, producing a flexible perception of duration that is both context-dependent and highly adaptive. The malleability of subjective time can also be seen in phenomena such as time dilation during high-stakes situations, where neural circuits are operating at heightened sensitivity. During moments of fear or exhilaration, the brain increases the rate of information sampling, amplifying the density of perceptual and mnemonic input. Neurotransmitters such as dopamine and norepinephrine play key roles in modulating these processes, influencing oscillatory activity and enhancing the salience of specific events. This mechanism explains why seconds can feel elongated in memory during emergencies or intense experiences despite their objective brevity on a clock. Temporal perception is not solely the product of isolated regions, but emerges from the dynamic interplay of neural structures across scales. The basal ganglia provide a rhythmic backbone, the cerebellum fine-tunes timing for precise intervals, and cortical oscillators synchronize distributed networks. Attention, memory, and emotion modulate the gain on these signals, producing the subjective sense of time that can stretch, contract, or flow seamlessly. Functional imaging and electrophysiological studies confirm that disruptions in any part of this network alter the perception of duration, demonstrating that our experience of time is a distributed emergent property of the brain's architecture. In practical terms, understanding these mechanisms sheds light on everyday experiences. When absorbed in an engaging task, oscillatory networks coordinate attentional focus and memory encoding, compressing perceived duration and creating a sense of time flying. During novel or emotionally charged events, increased neural firing and enhanced oscillatory coherence expand subjective time, allowing more detailed encoding of each moment. these effects are consistent across sensory modalities and cognitive domains, showing that the malleability of temporal perception is a fundamental property of neural function, not merely a psychological quirk. Ultimately, the brain's temporal mechanisms illustrate that subjective time is as much a product of biological architecture as it is of cognitive interpretation. The basal ganglia, cerebellum, and cortical oscillators form the core scaffolding, while attentional modulation, memory consolidation, and emotional salience shape the fine details of experience. This integration explains why time can feel elastic, flowing smoothly in one context and stretching dramatically in another, revealing that the experience of seconds, minutes, and hours is a living construction of the mind. By examining the neural foundations of temporal perception, we gain insight into the profound flexibility of human consciousness and the intricate ways in which our brains create the very fabric of lived time. Altered states of consciousness offer a unique window into the malleability of time, revealing just how flexible human perception can be. Practices such as meditation and mindfulness can expand or contract the felt duration of moments, allowing individuals to experience time in ways that deviate from ordinary perception. Experienced meditators often report that periods of focused attention on breath, body sensations, or a mantra can feel profoundly elongated, as though seconds stretch into minutes, while simultaneously fostering a sense of timelessness, where the boundaries between past, present, and future blur. This effect is not merely anecdotal. Functional neuroimaging studies reveal that these practices modulate activity within key networks of the brain, providing a physiological basis for the altered experience of time. Research by neuroscientist Robin Carhart-Harris has illuminated how psychedelic substances, such as psilocybin or lysergic acid diethylamide, influence temporal perception by altering activity in the default mode network. The default mode network, a set of interconnected cortical regions active during rest, self-reflection, and mind-wandering, is typically associated with the narrative continuity of the self across time. Under the influence of psychedelics, activity in this network decreases, reducing habitual patterns of thought and promoting a state in which the usual markers of past and future lose their rigidity. Subjects often describe moments as expanded, flowing without clear beginning or end, or as if time itself has dissolved. These experiences highlight the brain's capacity to reconstruct the experience of temporal flow based on neural network dynamics rather than external clocks. The phenomenology of these states shows a fascinating duality. Time can simultaneously expand and contract, depending on context, attention, and the richness of experience. In meditation, deep absorption allows the mind to anchor fully in the present, stretching subjective duration, while psychedelic states often dissolve the linear continuity of time, merging past, present, and future into a holistic awareness. Both cases illustrate that the brain's internal representation of time is highly plastic, responsive to attentional focus, sensory input, and the modulation of intrinsic neural activity. Experiments using electroencephalography and functional magnetic resonance imaging have demonstrated that both alpha and theta oscillations are altered during these states, corresponding with shifts in attention and the integration of sensory and mnemonic information. Altered temporal perception in these states also recalibrates attention, memory, and emotional processing. When time is experienced as expansive, attentional resources can be redistributed, allowing for heightened awareness of subtleties in sensory input or inner thought. Memory encoding can become richer, capturing nuanced emotional and perceptual details that might otherwise be overlooked. Emotionally salient events may be experienced with greater intensity and clarity, facilitating both insight and reflective processing. These alterations in neural timing networks reveal that subjective time is not a fixed metric, but a construct shaped by cognitive, affective, and sensory systems working in concert. Practical applications of these insights are increasingly recognized in mental health and creativity. Mindfulness-based interventions have been shown to improve anxiety, depression, and stress by modulating perceived temporal flow, allowing individuals to experience the present more fully rather than ruminating on the past or anticipating the future. Psychedelic-assisted therapy, studied in controlled settings at institutions such as Imperial College London and Johns Hopkins University, leverages the expansive sense of time to facilitate emotional processing and perspective shifts. Participants often describe breakthroughs that feel impossible within ordinary temporal constraints, suggesting that altering subjective time can support cognitive flexibility and therapeutic insight. Moreover, the expansion and contraction of perceived time during these altered states provide a natural laboratory for studying attention and consciousness. By observing how neural networks reconfigure, researchers gain insight into the mechanisms that normally structure temporal experience. The coordination between the prefrontal cortex, hippocampus, and parietal regions appears crucial for the continuity of subjective time, while modulation of these networks produces the striking temporal phenomena reported in meditation and psychedelic states. The resulting temporal elasticity demonstrates that the brain constructs time dynamically, integrating internal and external cues to produce a coherent, if flexible, sense of duration. Time perception under altered states also challenges our ordinary intuitions. When moments feel both prolonged and timeless, the boundaries between discrete events dissolve, emphasizing that our habitual experience of seconds, minutes, and hours is a product of standard neural activity rather than an absolute feature of reality. This aligns with earlier observations in quantum and information theoretic frameworks, suggesting that time emerges from relationships, processing, and observation rather than existing independently. In practical terms, these states reveal that temporal experience can be calibrated, enhanced, or even partially suspended, offering a window into the fundamental processes that shape consciousness itself. Interestingly, both meditation and psychedelics appear to operate through modulation of neural rhythms that govern attention, memory, and sensory integration. The slowing or desynchronization of oscillatory networks allows for a wider window of temporal integration, producing a sense of expanded duration. Conversely, heightened synchronization in specific bands can compress time, illustrating that subjective temporal elasticity depends on dynamic patterns of neural activity rather than static mechanisms. In this sense, the brain acts as both clock and observer, continuously constructing the felt flow of time based on context, physiological state, and cognitive priorities. Ultimately, examining altered states demonstrates the profound flexibility of human temporal perception. Moments can be elongated or collapsed. The continuity of past and future can blur, and attention, memory, and emotion can be recalibrated to create novel experiences of duration. Meditation and mindfulness cultivate these abilities naturally, while psychedelic states reveal the underlying neural mechanisms in more pronounced ways. Both pathways highlight that time, as experienced, is not a fixed quantity, but a living dynamic phenomenon shaped by the brain's architecture, its oscillatory networks, and the richness of present-moment awareness. Through these insights, we gain not only a deeper understanding of the mind, but also practical tools for mental health, creativity, and the cultivation of conscious experience, appreciating that the flow of time is as much a product of perception as it is of the ticking of clocks. In the modern world, the experience of time has become intimately intertwined with technology, often in ways that compress, fragment, or distort our perception of moments. Smartphones, social media platforms, and multitasking environments constantly compete for attention, creating a dynamic where temporal awareness is continuously interrupted. Researchers like Gloria Mark at the University of California, Irvine, have explored the effects of these digital environments on attention and the subjective experience of time. Her work shows that frequent task switching, notifications, and digital interruptions fragment focus, making it difficult to maintain a coherent sense of elapsed time. Moments that would otherwise feel continuous can become disjointed, and hours can seem to vanish unnoticed in a cascade of alerts, messages, and feeds. The neural impact of these fragmented experiences is significant. Overstimulation from constant digital input affects neural plasticity, altering how attention networks, memory circuits, and sensory processing interact. When the brain is bombarded with multiple competing streams of information, oscillatory networks responsible for temporal integration, particularly in the prefrontal cortex and parietal regions, must operate at a heightened pace. This leads to a compression of subjective time. Experiences feel shorter, attention becomes divided, and the continuity of events is disrupted. Studies in cognitive neuroscience suggest that these adaptations may improve certain rapid response skills, but can reduce the depth of encoding for long-term memory, subtly changing how time is experienced and recalled. digital time compression also affects cognitive and emotional processing. Rapid switching between tasks and the constant presence of digital stimuli can create a sense of urgency, reinforcing linear, clock-driven thinking while diminishing the experience of temporal expansiveness. In practical terms, this means that a day filled with continuous notifications, emails, and social media interactions can feel both overwhelming and fleeting, as the mind struggles to integrate fragmented temporal cues. The paradox is that while more information is processed, less of it is retained meaningfully, producing the impression that time is passing quickly even when little substantial progress has occurred. Strategies for regaining temporal presence in a hyper-connected world involve both behavioral adjustments and mindfulness practices. Setting boundaries around technology use, scheduling periods of focused, uninterrupted activity, and intentionally engaging with the present moment can recalibrate attention networks. Techniques such as time blocking, digital detoxes, and mindful observation of environmental cues help restore continuity to subjective temporal experience. Research indicates that even brief periods of sustained attention without technological interruption can reset oscillatory networks, improve memory encoding, and enhance the perception of temporal flow. By creating these structured pauses, individuals can counteract the fragmented temporal experience common in digital environments. Understanding the relationship between digital habits and subjective time also reveals broader cognitive principles. When attention is divided, the brain relies on rapid heuristic processing rather than deep sequential encoding, compressing the subjective passage of moments. Conversely, engagement in novel or immersive tasks within digital environments, such as interactive simulations or creative work, can expand temporal perception, demonstrating that the effects of technology are context-dependent. The key lies in the interaction between attentional focus, cognitive load, and environmental structure, illustrating that our experience of time is a flexible, emergent property influenced by both neural mechanisms and external stimuli. Anthropological and behavioral research further supports the idea that technology shapes temporal perception. Studies have shown that individuals immersed in continuous digital environments often underestimate the passage of time, a phenomenon sometimes referred to as digital time distortion. Conversely, intentionally limiting exposure and structuring interactions can create a more vivid sense of duration, aligning subjective experience with objective clock time. These findings emphasize that our temporal awareness is not fixed but adaptive, responding to environmental conditions, attentional demands, and the pace of information flow. In addition to attentional fragmentation, the emotional consequences of digital interaction play a role in shaping time perception. Social media notifications, news updates, and instant messaging can generate brief spikes of arousal, producing minor temporal dilation in the moment while contributing to overall compression when the day is retrospectively recalled. These micro-arousals interact with memory systems, affecting how experiences are encoded and later reconstructed, reinforcing the idea that time is both experienced in real time and reassembled through memory. The combination of fragmented attention, rapid stimulation, and emotional modulation produces a complex, often paradoxical temporal landscape in digital life. Ultimately, examining technology's influence on the mind reveals that subjective time is deeply sensitive to both cognitive and environmental structures. Digital tools, while providing immense connectivity and information access, challenge the brain's ability to maintain coherent temporal awareness, compressing subjective duration and fragmenting experience. However, through intentional engagement, attentional control, and mindful structuring of interactions, it is possible to recalibrate neural networks, restore temporal continuity, and enhance both memory and emotional processing. In this way, we see that the elasticity of subjective time is not merely a biological or psychological phenomenon, but is also shaped profoundly by the tools, rhythms, and environments we inhabit, offering both challenges and opportunities for regaining a sense of temporal presence in the digital age. Philosophy has long wrestled with the nature of time, offering frameworks that challenge intuition and expand the ways we think about past, present, and future. One influential perspective is presentism, the view that only the present exists. According to presentism, the past is gone, the future is yet to come, and reality consists solely of the ever-unfolding now. From this standpoint, the moment you're experiencing is the only one that's real, and all temporal experience is grounded in immediate perception. This aligns closely with everyday intuition. We remember the past, but it no longer exists, and we anticipate the future without being able to touch it directly. Presentism emphasizes the fleeting nature of experience and highlights the importance of attention and mindfulness in our conscious lives. By contrast, eternalism proposes that all points in time, past, present, and future, exist equally, much like different locations in space. In this view, events are fixed within a four-dimensional space-time manifold, and temporal passage is a feature of consciousness rather than an objective property of the universe. Philosophers and physicists alike have considered this framework, as it naturally accommodates relativistic physics, where simultaneity is observer-dependent and there is no universal now. According to eternalism, the events of your life, from birth to old age, coexist in space-time, and the sensation of flow emerges from your perspective moving along this temporal dimension. It is a radical departure from presentist intuition, but it resonates with findings in relativity and quantum theory, where time does not operate uniformly for all observers. Building on these ideas, the block universe theory treats time as a fixed, unchanging four-dimensional structure, where all events, past, present, and future, are embedded within a space-time block. Within this framework, change and temporal progression are emergent illusions, created by consciousness moving along the temporal dimension. Philosophers such as Hugh Price have explored the implications of time symmetry, emphasizing that the fundamental laws of physics do not privilege a direction of time. The apparent flow arises from boundary conditions and entropic considerations. Carlo Rovelli, working at the intersection of relational quantum mechanics and cosmology, has argued that temporal ordering is relational, emerging from interactions rather than existing as an absolute property. These perspectives challenge us to reconsider the notion of free will, as well as the causal links we intuitively perceive, suggesting that the universe may be more like a pre-written story than a sequence of unfolding events. The implications for causality and subjective perception are profound. If eternalism or the block universe perspective is correct, the sense of the present as moving forward is an emergent property of consciousness. Decisions, actions, and memories are experienced sequentially, but the temporal map in which they exist may be complete and unchanging. This raises questions about free will. If all events coexist, does choice exist? Or is it an internal experience of navigating a predetermined structure? While philosophy does not offer definitive answers, these frameworks encourage us to explore the relationship between subjective experience and the physical properties of the universe, bridging the gap between perception and objective reality. Neuroscience provides further insight into how these philosophical perspectives manifest in experience. The brain constructs the perception of temporal flow through interactions among attention networks, memory systems, and emotional processing circuits. Oscillatory activity in cortical regions, coordinated with subcortical timing structures like the basal ganglia and cerebellum, produces a coherent sense of past, present, and future. From a presentist perspective, these neural processes focus on the immediate now, updating representations in real time. From a block universe or eternalist perspective, they are mechanisms through which the mind experiences a sequential narrative, allowing a conscious agent to navigate a complex four-dimensional reality. The subjective sense of time, therefore, emerges from a combination of neural architecture, cognitive processing, and relational positioning within the external world. These philosophical frameworks also illuminate the nature of memory and anticipation. In a presentist view, memory reconstructs a vanished past, while prediction projects potential futures, both of which exist only as mental models. In eternalism or the block universe model, these reconstructions are reflections of existing temporal structures within space-time, encoded in brain networks that process and integrate events. The hippocampus, prefrontal cortex, and associated memory systems provide the scaffolding for this reconstruction, linking attention, emotion, and sensory information into a coherent temporal narrative. This intersection of philosophy, physics, and neuroscience underscores that subjective experience, while emergent, is deeply grounded in both biological mechanisms and the structure of reality itself. Time symmetry, a concept explored by both Price and Rovelli, offers additional perspective. At the fundamental physical level, many equations governing particle interactions are time reversible. They function identically whether time flows forward or backward. The asymmetry we perceive, the forward march of seconds and minutes, is largely a product of boundary conditions, entropy, and the relational positioning of observers within spacetime. Our brains, shaped by evolutionary pressures and biological rhythms, interpret these events in sequence, producing the experience of flow and change. Philosophical analysis complements this by highlighting that our intuitions about time's passage are contingent, not absolute, and that multiple coherent frameworks exist for understanding its nature. Engaging with these perspectives prepares us for a synthesis of temporal understanding. Presentism emphasizes immediacy and consciousness of the now. Eternalism situates us within a timeless continuum, and the block universe frames the cosmos as a fixed structure in which all events coexist. Integrating these views with insights from physics, cognitive neuroscience, and information theory allows us to appreciate both the flexibility and the constraints of subjective experience. It shows that the arrow of time, while perceptually linear, is embedded within a far more intricate multidimensional fabric where neural processes, physical laws, and philosophical interpretation converge to produce the sensation of moments flowing from past to future. Ultimately, exploring presentism, eternalism, and the block universe invites reflection on the very nature of existence and consciousness. By considering multiple models of temporal reality, we can begin to understand why time feels the way it does, why memories are structured sequentially, and why the future appears open even within a universe governed by deterministic or probabilistic laws. Philosophical inquiry, when coupled with empirical science, provides a lens through which we can reconcile subjective experience with objective reality, setting the stage for an integrated understanding of temporal perception, where the flow of time emerges at the intersection of physics, cognition, and consciousness itself. Time, as we have seen, exists on many layers, each with its own rhythms, scales, and mechanisms. From the probabilistic behavior of quantum particles to the vast sweep of cosmic expansion, from the precise oscillations of neural circuits to the fluidity of subjective perception, reality is structured across nested temporal frameworks. Each scale operates with its own metrics, yet these layers interconnect, forming a continuum in which local experiences emerge from global patterns. Understanding these interconnections allows us to synthesize quantum, cosmic, biological, and psychological time into a coherent, integrated picture, revealing that the universe is not measured by a single clock, but by a hierarchy of interacting temporal systems. At the quantum scale, particles exist in superpositions and are governed by probabilities rather than deterministic trajectories. Time in this realm is relational, emerging from interactions and observations, as emphasized by Carlo Rovelli in Relational Quantum Mechanics. The Wheeler-DeWitt equation further illustrates the timelessness of the universe at its most fundamental level, suggesting that classical temporal flow arises only as an emergent property from underlying changes in quantum states. Here, time is not an independent background, but a consequence of events and correlations, linking the passage of moments to the very structure of matter and energy. On the cosmic scale, time unfolds across billions of years, measured by the expansion of the universe, the movement of galaxies, and the cooling of the cosmic microwave background. Entropy increases, providing the thermodynamic arrow of time, while astronomical phenomena such as supernova, pulsar rotations, and gravitational lensing provide reference points for measurement. Seth Lloyd's work in information theory frames the universe as a vast computational system, where each event generates information and contributes to the forward progression of time. This perspective bridges the macroscopic sweep of the cosmos with the microscopic unpredictability of quantum mechanics, showing that both levels are part of a larger coherent temporal structure. Biological time operates on human scales, orchestrated by circadian rhythms, ultradian and infradian cycles, and neural oscillators. The suprachiasmatic nucleus coordinates daily rhythms, while the basal ganglia and cerebellum regulate sub-second and multi-second timing, allowing coordinated movement and perception. Attention, memory, and emotion modulate these processes, producing the subjective elasticity of time that characterizes lived experience. Research by Mark Whitman and David Eagleman demonstrates how neural networks integrate sensory, mnemonic, and emotional inputs to construct a temporal narrative, highlighting that subjective time, though different from cosmic or quantum measurements, is fully valid in its own right. Psychological time, then, is the layer through which humans interpret and experience all other scales. Moments expand or compress depending on novelty, attention, and emotional salience. Flow states, mindfulness, meditation, and even altered states induced by psychedelics recalibrate our perception of duration, revealing that conscious awareness itself is an instrument for experiencing time. Subjective experience is not an illusion, but a real, functional layer that enables adaptive behavior, memory encoding, and the appreciation of life's richness. Giulio Tononi's integrated information theory suggests that consciousness, by integrating information across networks, plays a central role in constructing temporal continuity and the feeling of now, linking subjective experience to measurable neural dynamics. The concept of nested temporal frameworks allows us to view these scales as interconnected rather than separate. Quantum indeterminacy influences microscopic events, which aggregate into macroscopic phenomena, producing the cosmic and biological patterns that humans inhabit. Biological clocks interpret environmental cues and coordinate internal rhythms, while cognitive processes impose narrative structure, creating continuity and meaning. In this framework, each level of time informs and constrains the others. Quantum fluctuations accumulate to form macroscopic outcomes, cosmic expansion provides context for planetary cycles, and neural oscillations translate external and internal events into perceivable flow. These layers are not isolated but mutually embedded, a hierarchy of temporal systems operating simultaneously across scales. Integrating these perspectives also highlights the legitimacy of subjective time. While atomic clocks, pulsar cycles, and cosmological measurements provide precise objective metrics, human experience offers a different but equally important perspective. The perceived stretching of moments, the compression of repeated tasks, and the emotional expansion of memorable events are genuine phenomena, reflecting the operations of attention, memory, emotion, and neural dynamics. A second felt under intense focus may seem longer than an objectively measured second, yet both exist within their respective frames, demonstrating that experiential and physical time are complementary rather than conflicting. This synthesis has practical implications for understanding cognition, decision-making, and well-being. Recognizing that time is layered allows us to appreciate why moments of high engagement or novelty feel expanded, why routine compresses perception, and why mindfulness practices can recalibrate our temporal awareness. It also informs scientific research. Psychologists, neuroscientists, physicists, and philosophers can collaborate across scales to examine how micro-level fluctuations produce macro-level patterns, and how these, in turn, shape subjective experience. Interdisciplinary approaches, drawing on the work of Lloyd, Tononi, Wittmann, and others, illuminate the nested complexity of time and provide a framework for integrating insights from diverse domains. Ultimately, time is not a single, uniform entity, but a multi-scaled tapestry in which quantum indeterminacy, cosmic expansion, biological rhythms, and subjective perception are woven together. Each layer operates according to its own principles yet resonates with the others, producing a coherent structure that supports life, cognition, and consciousness. By adopting a perspective of nested temporal frameworks, we can bridge the gap between objective measurement and subjective experience, between physics and psychology, and between observation and feeling. This integrated view underscores that the flow of time, whether measured by atomic clocks, observed in the cosmos, or felt in the heart of consciousness, is a rich, multidimensional phenomenon, offering profound insight into both the universe and the human mind. Living harmoniously with time requires awareness of both the objective, clock-measured seconds and the fluid, subjective experience of moments. Practices such as mindfulness and meditation can serve as bridges between these layers, helping individuals observe the present without judgment and recalibrate attention to align with both external and internal rhythms. By focusing on the breath, bodily sensations, or environmental cues, we anchor consciousness in the now, reducing the distortion of time caused by rumination on the past or worry about the future. Researchers in contemplative neuroscience, such as Richard Davidson and Antoine Lutz, have demonstrated that these practices enhance attentional networks, modulate amygdala activity, and improve integration of sensory and cognitive information, producing a more coherent perception of temporal flow. Introducing novelty into everyday experiences is another effective strategy for harmonizing subjective and objective time. When the brain encounters new stimuli, whether through learning a skill, exploring an unfamiliar environment, or engaging with creative tasks, attention is heightened, neural encoding becomes richer, and subjective time often expands. This principle, observed in studies of episodic memory and novelty detection, allows individuals to experience the fullness of moments more vividly, counteracting the compression that can occur in repetitive or routine environments. Incorporating periods of exploration or deliberate creativity into daily life recalibrates internal clocks and restores a sense of temporal richness, supporting both cognitive flexibility and emotional engagement. Pacing, too, is central to managing time perception. Overcommitment, multitasking, and constant digital stimulation, as highlighted in research by Gloria Mark, fragment attention and accelerate perceived time, often leaving individuals feeling rushed or fatigued. By structuring periods of focused work interspersed with breaks, we allow neural oscillatory networks to reset, facilitating optimal attention, memory encoding, and emotional regulation. Practices such as the Pomodoro technique or scheduled intervals for reflection and rest help align subjective experience with objective measures, producing a sense of control and coherence in daily routines. This mindful structuring of time supports productivity without sacrificing the quality of experience or emotional well-being. The interplay of these strategies has direct implications for mental health. Chronic stress, anxiety, and cognitive overload distort temporal perception, compressing the felt duration of routine activities while exaggerating moments of acute pressure. Mindfulness, novelty, and pacing help recalibrate these perceptions, mitigating stress responses by modulating amygdala activity and enhancing prefrontal cortical regulation. Improved temporal awareness correlates with greater emotional resilience, reduced anxiety, and enhanced capacity for planning and reflection. Similarly, subjective temporal expansion through immersive or creative activities contributes to a sense of fulfillment and presence, counteracting the flattening of experience that can accompany monotonous routines. Creativity benefits as well from harmonizing temporal scales. Time perception shapes how we structure ideas, organize narratives, and anticipate outcomes. When subjective time is expanded through focused attention or novel engagement, individuals can explore ideas more fully, integrate complex information, and access insights that may be elusive in a compressed, distracted state. Giulio Tononi's integrated information theory suggests that consciousness, by linking diverse neural networks, provides the scaffolding for rich temporal awareness, allowing creative processes to unfold across scales of seconds, minutes, and hours in ways that are both coherent and flexible. Reflection on the richness and variability of temporal experience also encourages a deeper appreciation of life's nuances. Just as cosmic expansion, entropy, and quantum fluctuations shape objective time on large and small scales, our internal experience of time is shaped by attention, memory, emotion, and environmental context. Recognizing that subjective time is as real and meaningful as physical time allows individuals to approach daily life with curiosity, intentionality, and acceptance. It reinforces the notion that moments of engagement, novelty, or reflection are not fleeting mistakes, but essential components of a meaningful temporal landscape. Practical strategies for living with time's fluidity extend beyond mindfulness and novelty. Intentional reduction of digital distractions, structured journaling, creative expression, and environmental modulation, such as exposure to natural light or rhythmic music, support neural oscillations that underpin temporal perception. Attention, emotion, and memory converge in these practices to produce a coherent sense of duration, bridging subjective experience with measurable time. In this way, we are not at the mercy of external clocks or internal drift, but can actively shape how time is perceived, remembered, and integrated into daily life. Ultimately, cultivating harmony with time invites a calm, reflective stance. By attending to attention, integrating novelty, pacing activity, and engaging with creative or immersive experiences, we align subjective and objective temporal scales, enhancing well-being, productivity, and presence. Each moment becomes both a measurable interval and a lived experience, dense with sensation, thought, and emotion. In the quiet of awareness, the seconds tick in concert with the rhythms of the mind and body, revealing a layered, fluid, and interconnected temporal reality. By recognizing this richness, we can move through life with greater calm, deeper engagement, and a profound appreciation for the varied textures of time itself. Time is a concept that threads through every layer of reality. From the probabilistic dance of quantum particles to the vast arcs of cosmic history, from the oscillations of neurons in our brains to the ebb and flow of our daily experiences. Physics, neuroscience, psychology, and philosophy each offer unique lenses through which to understand it, yet when viewed together, they converge into a rich, multi-dimensional tapestry. Classical mechanics provides the framework of measurable seconds and predictable motion, while Einsteinian relativity reveals that time stretches and contracts depending on velocity and gravity. Thermodynamics introduces the arrow of time through entropy, and information theory, as explored by Seth Lloyd, situates temporal flow in the generation and transformation of information. At every scale, time is dynamic, relational, and interwoven with the processes of the universe. Neuroscience shows us how time is constructed within the mind. The basal ganglia, cerebellum, and cortical oscillators coordinate sub-second and multi-second timing, integrating sensory input, attention, memory, and emotion to create a seamless temporal experience. Researchers such as David Eagleman and Mark Whitman have demonstrated that subjective time is malleable, stretching during novel or high arousal events, compressing under routine or distraction. Biological rhythms, including circadian, ultradian, and infradian cycles, anchor subjective experience, while memory and attention shape how we reconstruct the past and anticipate the future. Even altered states induced by meditation or psychedelics reveal that time is not a fixed property, but a living dynamic aspect of consciousness. Psychology and culture further illustrate the fluidity of temporal perception. Anthropologists and cognitive scientists have documented how societies perceive and structure time differently, from linear frameworks emphasizing schedules and deadlines to cyclical or polychronic cultures that experience duration more flexibly. Technology, multitasking, and digital environments can fragment attention, compress subjective time, and alter the integration of experience, yet mindful engagement, novelty, and pacing can restore coherence and richness to temporal awareness. Our lived sense of time is shaped by these internal and external influences, making subjective experience both real and meaningful, even when it diverges from physical measurement. Philosophical frameworks, from presentism to eternalism and the block universe, invite us to reflect on the fundamental nature of time itself. Presentism emphasizes the immediacy of the now. Eternalism situates us within a continuum where past, present, and future coexist. And block universe theory suggests that temporal flow emerges from consciousness, navigating a fixed space-time structure. Insights from Hugh Price and Carlo Rovelli illustrate that time may be relational and observer-dependent, aligning with both physical theory and the phenomenology of lived experience. These perspectives underscore that the perception of time is deeply intertwined with cognition, attention, and awareness, linking philosophical reasoning with empirical science. Bringing these threads together, we see that subjective time is as valid and significant as objective time. The elasticity of experience, moments that linger, rush, or bend, reflects the brain's integration of memory, emotion, attention, and neural oscillations. It is shaped by biology, culture, and environment, yet it is fully real as lived experience. Recognizing this encourages curiosity and mindful engagement, inviting us to observe how seconds and hours expand, contract, and acquire meaning in our consciousness. By attending to temporal flow, we deepen not only our understanding of the universe, but also our appreciation for the richness of our own lives. As we reflect on these perspectives, it becomes clear that time is neither a rigid metric nor a single, unchanging stream. It is layered, relational, and dynamic, experienced uniquely in each mind while simultaneously governed by physical laws that shape the cosmos. The quantum, cosmic, biological, and psychological scales are not separate but nested, interacting to produce the full spectrum of temporal experience. Moments of insight, creativity, or heightened attention reveal how subjective perception can stretch, while repetitive or distracted intervals demonstrate how it can compress. In this way, every instant carries depth and texture, revealing the subtle interplay between the measurable and the felt, the external and the internal. Time, in its mystery and beauty, invites wonder. Its elasticity allows us to savor experiences, to expand perception during novelty or excitement, and to integrate the past and future into meaningful narratives. By observing how physics, neuroscience, psychology, and philosophy converge, we appreciate that time is both a framework for understanding reality and a canvas upon which consciousness paints experience. As we sit with this reflection, we can notice the gentle rhythm of our own awareness, the flow of moments that are at once fleeting and infinitely rich. In acknowledging the interplay between objective and subjective time, we cultivate a sense of calm, curiosity, and deep appreciation for the remarkable, multifaceted nature of temporal experience itself.